Hey guys, this is Srini and you're watching Python tutorials on my channel Python for Microscopists on YouTube. In today's tutorial, let's actually have a look at a few denoising filters, image denoising filters, because oftentimes in microscopy, we have to make a choice between speed and signal to noise. And of course, you want to collect publication quality images, but not all the time. You just for most of the time, you want to collect images so you can extract relevant information. What is the distribution of mitochondria or nuclei in your images, or inclusions if you're looking at material science samples, different minerals if you're looking at geological samples. So eventually you would like to quantitatively extract some information from your images, so you don't really need all that high signal to noise. So if you can get the same information from low signal to noise, why not go ahead and do that? So whether you want it or not, there will be some noise in your images. Sometimes it's worse. So how do we clean those images up? Okay, so this is exactly what we're going to look at in our today's tutorial. But what I should also mention that digital filters are nothing but a convolution between a kernel and your image. When I say a convolution, that's nothing but a multiplication of two arrays that are of different size. Okay, a kernel is, let's say, a small matrix. Let's say the matrix is 3 by 3 matrix with some numbers in there, and your image is a much larger matrix with a whole bunch of numbers in there also, right? So we do this convolution by multiplying these two arrays. Now the kernel can be a linear filter, let's say, or a linear kernel like in a Gaussian kernel. And I'm going to talk about that in a second, Gaussian. And the other type of filter that they call it linear filter. And one example is a median filter. And typically non-linear filters preserve edges. And again, we'll demonstrate that in a minute. And median filter can be a great filter that actually does preserve the edges and then cleans up the image a little bit. My personal favorite denoising filter is called non-local means denoising, and you can get actually more information about non-local means from if you just Google search for scikit-image and non-local means, you'll find a page where it kind of talks about what it exactly does. Yeah, instead of local means, this is non-local means. Okay, that's the difference between these two algorithms, and we'll look at these three today using a microscope image example. So let's jump in. And this is my Spider IDE, which is part of Anaconda distribution. My personal favorite because it comes up, it comes pre-packaged with all needed libraries for image processing. First of all, let me go ahead and copy and paste some code that I have here to demonstrate the Gaussian kernel, like how does a Gaussian kernel looks like. So let's not worry about how to write this code. This is not part of what we want to do today. And based on this setting, actually let's change this to 1 so you can see a 3 by 3 matrix. And here, let me scroll up. As you can see, this kernel is nothing but a 3 by 3 matrix or array with numbers ranging from 0.04 to 0.33. And one thing you should notice is when you add all these numbers up, they should add up to a value of 1. That's because when you convolve an image with a kernel, you don't want to change the energy of the image. So by multiplying it by 1, you're not changing the energy of this original image. Okay? So if you actually select a Gaussian kernel here, excuse me, now you can see this is a bigger kernel, and also the value at the center is high, and as you go from the center and out, the value drops down. So the Gaussian, as the name suggests, is nothing but, or one-dimensional Gaussian is like a bell-shaped curve. This is a two-dimensional Gaussian, so think of this as a hill. Okay? At the top, in the center, you have a high value. As you taper down, the value goes down. So this is a Gaussian kernel, and similarly a median kernel, you can define the size of it. It can be 3 by 3, it can be 5 by 5. A median kernel, as the name suggests, it just takes the median value within that window, within that size. So let's go ahead and apply some denoising to an image, and the image I plan on using today is called well, I'm calling it noisy image, but this is a light microscope fluorescence image, and you can see if I zoom in there is a lot of noise, and we want to preserve the edges. We'll get to that in a minute, but let's go ahead and start with first of all reading the image and then applying Gaussian filter. So we know how to read the image. First of all, we need the right library from Sciki-image, import IO, and then my image equals io.imread, and my picture, my image is in images. Let me just double confirm it one more time. Denoising, and it's called noisy image .jpg. Okay, so we are done reading the image. Now we need to apply. Well, let's close it. Okay, so now we need to apply Gaussian denoising, and that's actually part of SciPy ND image. So let's go ahead and import the right library. So let me go back up from SciPy, import ND image as ND. Okay, so now I can just go ahead and convert. So let me define again a parameter Gaussian underscore image, a variable Gaussian underscore image, which equals to, we are importing ND, and when I hit dot, it's prompting me with what I can do. There are so many, binary erosions and all of these. What I want now is Gaussian filter right there. That's it. Of what? Of my image, and then sigma. Let's just use a sigma of 3. That's it. Okay. And now we can go ahead and plot and then show the image right here. But since we are looking at noise, we may not be able to separate or compare the two images, the original and the denoised image in this little window on the right hand side. So let me go ahead and save it. So first of all, we need to import the right library. So from matplotlib dot pyplot, well, import pyplot as plt. Okay. So let's save this. So I'm going to call this plt.imsave, and let's save it under the same directory, images denoising / let's just call this Gaussian, if I can type correctly, Gaussian.jpg. Okay, and then the image name is Gaussian underscore image. So we are saving this image as Gaussian.jpg. So and it's saying something about my Gaussian underscore image undefined name. So I misspelled it here again. At least one mistake per video. So that's the first one. Okay, so now let's go ahead and run this. It should take a few seconds. It says no such directory. Again, this is my second mistake, I guess. Images denoi. Let me go back. Sorry about this. images, and then denoising, denoisi. It's noisy image. So what did it say? No such. Oh, maybe I made a mistake down here. Oh, same line, 2 mistakes. Again. Let's hope this works. Okay, there you go. It's done. So let me go ahead and open the folder, and there is another image right there. Let's not worry about why it is grayscale. And let's open the noisy image. Let's open the denoised image and compare these two. Okay, so this is my Gaussian, and yet, as you can see, it's pretty clean. I mean, let's zoom in again and look at one small region, and let's also zoom in here, pretty much the same region. You see that is very clean, but at the same time the image is completely blurred, and we are losing information here. The edges are not preserved, so that's why Gaussian filtering is typically not preferred. So let's go back and do our median filtering. Okay, and median is, since we are importing ND image, median image is nothing but ND dot, when I type median, there you go, median filter. And let's do the same image here. Oh, never mind. img and nd dot median filter, and again if we do this again it should prompt img, and this time it's not sigma, the second parameter is size, and this is the size of the window, of the kernel, so let's keep the size to small, like 3 by 3, and let's go ahead and save this image also so we can compare all three at the same time. So this is median, this should be median. Okay, so let's go ahead and run this, and there you go. I have a median image, and let's go ahead and open it and compare it with our original image. Again, let me and let's minimize this. Okay, so as you can see, now this is much better than Gaussian already. When I zoom in, you should be able to see, sorry about that. Now I have many of these, so okay, there you go. And now let's zoom into this image, and you can actually see that the edges are perfectly preserved. Yeah, and the image is denoised. I mean, I still see something going on here. If I change the median value to 5 or something, let's close all images. Okay. Let's close all. Now change the median value to 5. Let's change the sigma to 5, and then just compare these images one more time. Okay, so these should be the new images now, and this is our original image, should not change, and this is our Gaussian image, should get blurrier. As you can see, this is very blurry now. Of course, the central pixels are very clean right there, compared to the original image, but at the same time we lost a lot of information that's contained in the image. So what we learned here, Gaussian, try not to use it. Median filter with a kernel size of 5. With 3, I was very happy. I'm getting a bit greedy here, so I just wanted to see how 5 actually looks like. I think I started to kind of lose some information from edges, and the center didn't improve by a lot, but it did, improve a little bit. So to me, the kernel size of, or the kernel size of 3 definitely makes sense for both of these filters, if you would like to use them. So finally, let's finish this off by looking at the non-local means filter, and we already looked at the information here on this website, scikit-image non-local means documentation. And if you scroll down, the good thing with most of these filters, the documentation is pretty amazing. We just need to copy the code, and do not feel guilty copying code, especially look at the licensing, and if the licensing is good enough, copy the code, because do not waste your time reinventing all this code again. Okay, no point in proving yourself as a genius. Use the code that's already there, and customize your the code for your specific application. Okay, so let's go ahead and look at exactly how this works. This is nothing but one line, denoise NL means, and we need to supply the input image and all the required parameters in here. So I'm going to copy and paste right there, and I do not want to give my input this way. In fact, I want to give my, all it's doing here is, this is a placeholder for patch KW, and all it's doing is 2 stars. It unwraps this dictionary into here. It's equivalent to typing patch size equals to 5 equals to 6 and multi-channel equals to true inside this the parameters input space. So let's do exactly that. So I'm going to use patch size equals to 5 and put it inside here just for the fun of it. Patch underscore distance equals to 3, and what's the other one? I think it's multi-channel and equals to true. Let's do multi-channel equal to true, and then close this. And obviously we need the right libraries. Denoise NL means is in what library? Oh, sorry, right there. Denoise NL means and estimate sigma are part of this restoration package library. And estimate sigma, this is one of the parameters that actually goes in here. So let's actually see how it's done here. So sigma estimate is nothing but the mean, and then you estimate the sigma over there. So in the mean uses numpy, so let's go ahead and import numpy as np. Okay, so we are importing numpy, so that should be good. And our image is not called noisy, our image is called img. So let's fix that. Let's fix this here, and we should be we should be good. Now obviously we want to save this image, so let me copy this line and paste it right here, and we want to call this NLM, and let's call this NLM, which means I do not want to call this denoise here, I want to call this NLM. Okay. Now one thing I would like to mention here, if you look at fast mode equals to false, which means it uses the slow mode obviously, but I've done a bit of testing on the final image quality when you use false, fast mode equals false and true. I couldn't tell the difference. And I also performed some image processing, and the computer couldn't tell the difference based on the results that I've got on the samples I've tested, on the images I've tested. So I tend to use fast mode equals to true. It saves tremendous amount of time. Between false and true, based on the images I tested, there is at least an order of magnitude difference. If this one takes 0.3 seconds, then the fast mode, the equals to false, actually takes anywhere from 3 to 10 seconds actually. So depending on the image. So if you have 100 images, you'll save tremendous amount of time by putting fast mode equals to true. So let's go ahead and run this and look at our final images. And let me open this. NLM, I don't see much of anything here. It didn't do a good job, and I think I know the reason why. When you're doing math to your images, some algorithms convert them into the right format and all of that, you know. So it's always a good idea to make sure you are converting your images into float. If I bet when we go to Variable Explorer, you can see our image is a unsigned integer 8, which means the values go from 0 to 255. Let's convert this into a float. So image as float. This converts this image into float, and this function is part of scikit-image. So let's go ahead and import that image as float. And you can always convert the image back to 8-bit when you're done at the last step. But let's convert this and see if that actually improves our result. Well, we didn't have any results, just a bunch of noise. And now you can see I have something right here. So let's go ahead and open the original file. And by the way, we left multi-channel equals to true. That basically means if my original image is a color image, go ahead and give me a handle all the 3 channels. So I got a color image as my NLM output here. So let's compare these two. We've already compared median and Gaussian, so let's not worry about it for now. And let's go ahead and zoom onto this one, what looks like a nuclei. And let's also zoom onto this on this other side. And you can see the edges are perfectly preserved. The noise is cleaned up. Okay, and we still have all the original information here. And this image on the right hand side now is ready to be segmented using our favorite segmentation process. So here it is, the 3 denoising ways, and I already mentioned that the non-local means is my personal favorite because whether it is a CT image or a light microscope image or an electron microscope image or a TEM image, it doesn't matter if you have a noisy image, this NLM, in fact, even if it is a camera image with high ISO, try this non-local means filter on a digital camera image taken at 1600 or even higher ISOs where you have a lot of noise. This actually does an excellent job. So anyway, this is a quick tutorial on denoising filters in Python, and in our next tutorial, let's learn something new, something different. I hope you found this tutorial useful. Please go ahead and subscribe to my channel for regular updates, and thank you very much for your attention.